Hello, Chem 116 students. I thought I'd give you a few more minutes of conversation about the end of Activity 4. We didn't have time to discuss this in detail in class. The reverse of alcohol dehydration can be honestly seen as alkene hydration. This catalyst is the same. And so what bonds are broken and what atoms are added in these reactions? Well, this should be a review of things that we talked about before. But again, you're breaking the double bond and you're adding something at each place where the bond was broken. And so in the first example, you're putting on the OH and the hydrogen on adjacent carbons to make the alkene into an alcohol. The second example, and these should be very familiar from previous activity, is again breaking the double bond and you're adding the hydrogen and the OH to make an alcohol. But this time, owing to the fact that there is the same number of hydrogens on the two carbons of the double bond, the OH group can go on either carbon of the double bond. You can't determine, Markovnikov's rule does not give you a major product here because the two carbons of the double bond have the same number of hydrogens. So it can go in two places, giving you two possible products. And then the third example here, you break the double bond, you add hydrogen and OH. This time, where does the OH go? The OH goes to the side that has the fewest hydrogens, so it's going to be on the right carbon in this example, and resulting in the product shown at the right, where you have another alcohol. The hydrogen that's added doesn't look like anything special because it's just hydrogen, but it's there all the same. Again, just to remind you, on the first example here, the hydrogen on the 1-pentene was added to the 1-pentene on the left carbon because it is the carbon that has the fewest hydrogens, in this case only one compared to its neighbor that has two. Alright, so having said that, what next? If we're looking at these reactions and comparing them to the alcohol dehydrations from Model 1, are these reactions the exact reverse of one another? Well, if you take 1-pentene and hydrate it by adding water, you end up with 2-pentanol, which we just saw in the previous slide. Because of Markovnikov's rule, the alcohol is going to go on the second carbon. But if you took 1-pentene, if you took 1-pentanol, you don't necessarily get the same reverse reactions. So these aren't exactly the reverse of one another because you have 2-pentanol produced from the dehydration and the 1-pentanol from hydration, and 1-pentanol is the results in 1-pentene. So you have two different alcohols connected to the alkene in this example. Not quite the same, similar, but not quite the same. The second pair is 2-pentene being hydrated compared to how do you dehydrate an alcohol to make 2-pentene? Well, in this case, 2-pentene hydrates to make two products, 2 and 3-pentanol both, and so there's two products. But if you're going to take 2-pentanol and dehydrate it, then the product becomes 2-pentene. So it's nearly the same in reverse, but the forward reaction of adding water results in two products, so they're not exactly the same, but some parts of it are the same. The third comparison from Model 3, if you followed through here, has 2-methylbutene, 2-butene being hydrated to make 2-methyl-2-butanol, which is exactly the same thing as reversed when you take 2-methyl-2-butanol and take away the water to make 2-methyl-2-butene. So in this case, yes, but the other examples aren't exactly reversed. They're close, but not exactly the same. So if you read carefully, and these paragraphs are here for your benefit, alkenes are always going to undergo addition reactions as far as we're concerned, where two carbon atoms are added to the carbons of the double bond, resulting in a product that is no longer unsaturated. We've done this. And the two atoms that are being added are these reagents in the first column of Table 1. They may be identical as they are, where they're either hydrogenation or halogenation, or they may be two different entities, like when you add water or hydrogen halides. So if you have those things added to alkenes. This is completely review from the previous chapter, by the way. You get products that are all some kind of saturated compound, and Markovnikov's rule will be used when we're trying to decide where to put the hydrogen in the latter two examples, where there's hydrogen with a second atom or group being OH. So Markovnikov rules tells us that the hydrogen is being added to the carbon bound to the most hydrogen atoms. You should recall this, I hope. All right. So a little bit of a summary. What important concepts were covered in this activity? You should know more about how alcohol dehydration occurs. Remember that you're going to lose hydrogen and OH from adjacent carbons when dehydration occurs. Two adjacent atoms lose something, and they end up making a double bond between them. The hydrogen is going to be lost from the carbon with the fewest hydrogens. It sounds a little tricky to say it, but it's exactly how you need to think of it. And if there's a choice, sometimes there's not. When alcohols oxidize, it depends on their type, whether they're primary, secondary, or tertiary. And if it's an alcohol that's primary, it's going to be two steps. The first step for either one will be losing two hydrogens. If it's primary, then it have a second step where an oxygen is going to be added. So again, losing two hydrogens with either a primary or secondary alcohol, they're going to be lost from adjacent atoms, and those two adjacent atoms are going to end up making a double bond between them. We call that a carbonyl, and it results in the functional group of either being an aldehyde or a ketone, depending on whether it was a primary or secondary alcohol. Tertiary alcohols do not oxidize, no reaction. And so we need to be aware that alkene hydration and alcohol dehydration are very similar because they use the same catalyst, and sometimes the reverse of hydration looks like dehydration, but not 100%. All right, a couple more things to cover just as some extra pieces for this chapter. Pause just a minute here, that's not where I was going. What I meant to show you is some extra examples of oxidation, and if we had time to do all these in class, we could split them up, but we're not going to. So let's talk about it instead. If you oxidize these alcohols, what are we going to do? So an alcohol in this case would be 1, 2, 3 carbons. It's a primary alcohol. The primary alcohol is always going to turn into an aldehyde. So keep it as simple as possible by remembering that the carbon chain is basically unchanged. It's the alcohol that's affected, because only until we came onto alcohols do we have this new possibility. And so you're going to lose a hydrogen from the oxygen and one of the hydrogens off of its neighboring carbon, resulting in a double bond O. We call that an aldehyde. And if it continues to oxidize and there's nothing to stop it, or if we don't specify something in terms of milder conditions, the aldehyde will continue to be oxidized by adding the extra oxygen atom. The carbon chain again remains unchanged, and you still have 3 carbons with a double bond O at the end carbon. But now, instead of having just a carbonyl and a hydrogen, and oxygen is being added between the, I'm going to write it here carefully, a little bit crowded, between the hydrogen and the carbon, resulting in a carboxylic acid. Simple if you keep it straight, I hope. So make sure you remember the first step is losing 2 hydrogens, and the second step is adding oxygens. 1 oxygen, sorry. 2 hydrogens, always 2. And the second step in the case of the primary alcohol is you add oxygen. Now, the second example on this screen, we could name it if we chose to, but let's not do that for the moment. That might be an odd compound, honestly. And so the first thing we want to do is decide what type of alcohol it is to determine what type of product we're expecting to see. The alcohol carbon, in this case, is attached to 2 other carbons, so that makes it a secondary alcohol. We're going to get a ketone, and there will be no further oxidation than that. A ketone is as far as you will go for this example. How do we get there? Same way we did on the first one, where you lose 2 hydrogens. And so I'm just going to write 2 hydrogens. The rest of the carbon chain, we're going to get used to this gradually, is not affected by the oxidation process. So you just write it the way it was originally presented and realize what it's going to have to change. So if we're going to lose 2 hydrogens, where do we lose them? We're going to take one from the alcohol and one from the carbon with the alcohol. The result is that this oxygen now no longer has just one bond to carbon, but 2. We call that a ketone. And the methyl group on the end, in this example, is intact, no further change. Another reaction example. If we were to take those same 2 compounds and dehydrate them, think carefully how that works. In other words, we're going to use the sulfuric acid catalyst. I'm not going to write it in for the moment, but you know it requires a catalyst. We call that. And what are we going to lose? We're going to lose water. Well, water has to be lost in 2 components. We're going to lose the oxygen in the OH group, and also a hydrogen from adjacent atoms. So if you take the OH off this carbon, which is the only place you can go, you can't take anything more off of this carbon, so it has to be from the middle adjacent carbon. We'll take it off, and we will no longer have 2 hydrogens there. Let's draw it out. The carbon chain stays intact. The leftmost carbon hasn't been affected. The middle carbon will have lost 1 hydrogen, still has 1. The end carbon still has 2 hydrogens. We didn't take away those. But what has to happen, the 2 atoms that lost something now will make a double bond. It's an alkene. If you do a dehydration reaction of the second compound, which you certainly can, you're going to do the same idea as we see here, losing hydrogen and OH. Well, the OH is easy, but you have to lose them from adjacent atoms. So we're going to break that bond. But you cannot take the hydrogen here, so you're going to have to decide what your choices are. It's the neighbors to this carbon with the OH that have to be considered. So this carbon on the left has how many hydrogens? Stare at it for a minute and realize that it has 1, 2, 3 bonds shown, so the 4th bond is a hydrogen. And the carbon to the right on the end carbon has 3 hydrogens. Again, how do we do this? We're going to take the hydrogen from the carbon that has the fewest hydrogens. So therefore, we will take away the one that's the only one on that carbon of the ring. It looks funny, but you don't have to care. It works however the rules tell us. And so instead of having just a single bond to this carbon with this CH group here, let's draw carbon, and then a CH3, we lost the OH group, we keep a hydrogen, but this carbon needs another bond, and having removed 1 hydrogen of its neighbor, this is going to become a double bond. And no, we're not going to name this, it's kind of an odd compound. So there's an example again of making an alkene from the dehydration reaction of this compound.